Alrighty, and then to finish up our last two examples. So in example 3, the population of a city grows according to the differential equation below, where k is a constant and t is in years. This is the exact same differential equation that we've been working with. And that makes sense that the rate at which you are increasing, the rate at which you're changing, is going to be proportional to the number of people you already have. That checks out. The population of a city doubles every 12 years. What's the value of k? So they didn't really give us any numbers to work with, but we can kind of invent our own. So if it doubles every 12 years, well, let's talk about what's happening at year 0 and at year 12. Now, year 0, we don't know for sure exactly what the population was, but let's just call it P naught, right? Your initial population based on whenever you start keeping track of time. Well, if it doubles in 12 years, that means that you're going to have 2 times P naught in 12 years, right? Now, the way that we have our equation written, notice that our, and I guess, okay, I apologize. So we should technically go through the process of solving this differential equation. Hopefully you start to see that now and recognize really quickly that that just gives you your exponential growth function. So that's going to end up giving you y, although not y in this case, p equals ce to the rt or kt in this particular case because they give us the constant value to begin with. But know that that is what we would always end up getting when we solve that differential equation. It's never bad to go through the process of solving it, but since we just did that in the last two example problems, we'll skip it this time around. Because guess what? We're going to do it in the next problem. So we end up with our exponential growth function, and we know that at year 0, we end up getting, oh, I'm sorry, that's a value for t, isn't it? So e to the k times 0, c, and then that ends up giving us p naught, whatever our initial population is. Well, we end up finding that c is just equal to p naught, or p naught is the same thing as that initial starting value. So if you want to call it c, great. If you want to call it p naught, that's fine too. They actually end up being the same thing, which makes sense, right? At year 0, you would expect that you'd have your initial population, and the c is always what you're starting with. So further on, though, we need to plug in our next point, and that gives us a little bit more useful information, not more, but different useful. And we know that if we plug in e to the k times 12, and remember that initial value we were calling p naught, then after those 12 years, we're going to have double whatever we started with. Notice what happens as we try to solve for k. The first thing we do is we divide both sides by whatever that initial population was. Call it c, call it p naught, call it whatever you want. It ends up canceling. So we just have 2 equals e to the 12k. So as we solve for k, we just need to log loop it, right? So then log base e of 2 is going to equal 12k. So finally, to get k by itself, divide both sides by 12. Natural log of 2, all divided by 12, is going to give us our k value. We plug it into our calculator and find that it is closest to a. And lastly, in example 4, we want to translate the following and then solve the differential equation and determine the number of half-lives, oh boy, it will take for 100 grams to decay down to just 10 grams. Well, we are told that in radioactive decay, the rate of change of the material present is proportional to the negative amount. Okay, interesting. Well, based on what they told us, the rate of change of the material present, dy dt, is proportional to negative y. Well, we can still solve this, and it's still going to give us an exponential growth, quote-unquote, function. We'll talk about that in a minute. But we end up solving, and we still get an exponential function. So let's solve the differential equation by separating our variables. And then we need 1 over, now it doesn't matter where you put the negative. Let's go ahead and keep it on the right, and that means that it's actually going to be with the k then. So then multiplying both sides by 1 over y, we are still going to get 1 over y dy, which is great. And then on the right-hand side, we just get negative k dt. We integrate both sides. We get the natural log of, again, absolute value of y, but our absolute values won't be necessary because Y is related to the amount of material present. So let's just throw those out the window. And that is going to be equal to negative KT plus C. We log loop or exponentiate both sides. Either way, we get e to the negative KT times e to the c, which is just going to give us some new constant, is going to be equal to y all by itself. Now, notice that this is really pretty much the exact same function we had before. It's just a little bit different in terms of what is happening with our exponent on e, but a negative k, right? Remember that k is a constant. A negative constant is still just a constant. So this is the way that we were told, so this is the way we're going to set it up, but know that it's nothing super new or super wonky. So then they don't really give us anything else to help us identify C or what that K value might be. Well, we're told that we are dealing with half-lives. Oh boy, bringing back those memories. Well, remember that at time 0, if you have some initial amount, let's call it Y naught, then in one half-life, you are going to be left with half of whatever you originally had. In 2 total half-lives, you're going to be left with a fourth of what you originally had, right? You cut it in half each time. Now, as long as we let t be equal to the number of half-lives, this is all the info that we need to find out what that k value might be. So, and our c value, note, can technically change, right? Because c is your starting amount. Well, it's all related to how much of your amount you're starting with. In the particular problem they gave us, we're talking about 100 grams initially, but your K value is going to end up working no matter what you find, or no matter how much of a specific radioactive substance you start with. Fun fact. So from our first equation, we know that our C is going to be our Y naught, right? And then we also know from our second equation that 1/2 of your initial amount is going to remain after we are plugging in 1 half-life. We solve for k, because that's our goal, remember. Divide both sides by y naught, and they just end up canceling. So a half is equal e to the negative k. We log loop both sides. The natural log of a half is equal to negative k, or you can just go ahead and move that negative to the other side. So k is a negative natural log of 1/2, whatever that fun decimal may be. Now here's the deal though. You had that negative in your equation to begin with. So if you found that your k value is negative, and then you also had the negative right there, when you plug in k, we get y equals ce to the negative natural log of 1/2 times t. So all we're left with is a positive in our exponent. So we want to try and find out how many half-lives it would take for only 10%, or excuse me, for only 10 grams to remain if we started with 100. Well, 100 grams is going to go in for our C. So we have we have 100 e to the, I'm going to put the t in front so I don't need parentheses. And then we want to know how long it's going to take to be just left with 10 grams. So I kind of jumped the gun. So from here, we divide both sides by 10, or by 100. We're left with just 10% of our initial amount. So 0.1 equals e to the t times the natural log of half. And we can log loop both sides from here. So we will have the natural log of 0.1 equaling t times the natural log of 0.5. And then we divide both sides by the number attached to our variable, which is the natural log of 0.5. So when we do that and we just plug it directly into our calculator, we find that that's going to take us about 3.322, and remember our units for t, 3.322 half-lives. So that makes sense. If we're down to just 10%, well, after 1 half-life, you'd be left with 50%. 2 half-lives, you'd be left with 25%. 3 half-lives, you're down to 12.5%. So that makes a lot of sense that it's just a little bit more than 3 half-lives, however long that may be for any particular radioactive element. So we are going to come together tomorrow and discuss this a little bit more, especially in relation to some practice AP